Good. Welcome, everybody. We almost done with the course. It's lecture number 11. And what we will look at today will be interaction, right? We've been working with interaction for a while. Yes, it works more or less. Fine. Then let me go with the lecture. Tunneling in electromagnetic environment. So this is what we have already learned. It's a Coulomb blockade, it's interaction, but in a little bit different aspect. When we involve Coulomb blockade, we just charge certain island. Another possibility is to produce a wave of propagating charge in an electric circuit. We produce it by tunneling of an electron, and well, it propagates and it affects this tunneling rate. So in the first part of the lecture, we will investigate this effect, which is called dynamical Coulomb blockade. What we especially look at is to understand the suppression beyond perturbation limit. It appears to be that everything depends on the effective impedance of the resulting environment of the electric circuit where this junction is incorporated. And again, we encounter here our old acquaintance, conductance quantum. This is the measure of the impedance. So there are circuits with low impedance, smaller than inverse conductance quantum, and there are circuits with larger impedance, and those are cases of weak and strong interaction, respectively. Very good. So we will go through this. We will quantify this. We will look at IV curves of tunnel junction to limits. We will look at qubits in this respect. That will be about single electron tunneling. Then we look at superconducting devices. We investigate Cooper pair tunneling, understand the dynamics of Josephson junction in the presence of electromagnetic environment, and we will consider also a more exotic tunneling process. It's not tunneling of a charge, but tunneling of the phase in Josephson junction. Right, that more or less completes the topics. Next lecture will be about decoherence and dephasing. In this case, we also have an environment which affects quantum system, quantum electrons, or qubits. Right, so it will be a related adjacent topic. Fine, so let me formulate a simple setup. To work with, let me formulate a problem. So let us see. We have a tunnel junction, electrons tunnel through this junction. They would get to a place which in principle could be an island, is some capacitance, right? However, I add another element. I connect this island with with the ground by a resistor, with conductance G. Let us look at the limits. If this conductance is very large, well, it just short circuits the capacitance, short circuits the islands, and we just have tunneling between two leads, elastic tunneling. So we can picture like this in energy diagram. Electrons come from here. They cross tunnel barrier and they remain at the same level. If G is small, then it looks like the circuit is interrupted here. So we are back to setup we have already investigated. There is a Coulomb blockade island. And what does it mean? An electron, which comes here, should pay energy to energize the island. Consequently, it will go at lower energy. This reduces the width of energy strip available for tunneling. It suppresses, it blockades the tunneling rate. Good. So today we will investigate what is in between. Suppose G is not very large, not very small. What happens with the tunneling? Somehow we should connect these two opposite cases. Let me give you a sort of answer for this rather general answer. In this situation, an electron which tunnels experiences a stochastic energy loss. It's not zero like in elastic case. It's not Coulomb blockade energy as in Coulomb blockade case. It is some random quantity. And the probability distribution of this random quantity is given by this function P of I. Well, P stands for probability. Good. Suppose we know this function. We don't know yet, but suppose we know. How can we compute the current? Here's the answer. Let me just understand what are elements. So there's an electron coming at energy E, right? It has to be there, so it's proportional to feed-in factor at this energy. All right, it loses energy and it goes at energy E prime, and it has to find a place at this energy. So it's 1 minus F factor at this energy. And here's a probability. It just gives a probability of this energy loss. Right. So if we know this function, we know the tunneling rate, and we know the current. Fine. Let me explain how to evaluate this, how to get a notion of this probability function. To this end, let me modify electromagnetic environment for this tunnel junction. Instead of a resistor, I would just set an inductor. What does it mean? It means that that the tunneling electron feels an oscillator. This frequency is given by capacitance and inductance, and in this case, electron when tunnels can experience a quantized energy loss. It can lose different number of oscillation quanta. It can give to the oscillator quantized amount of energy. Right. So this is a distribution. It is a set of delta functional peaks, and we have discrete probabilities of emitting n quanta. Another element, another assumption which can be confirmed by computation is that these quanta, these probabilities, these quanta are emitted independently from each other. In this case, these probabilities are given by Poisson distribution. Here it is, where rho is a parameter of Poisson distribution, which is eventually average number of quanta which tunneling electron can emit. Right, one can estimate this average number of quanta, say as Coulomb energy, which it can spend at most, and this is energy splitting of oscillator levels. So that's how many quanta could go in average. Right. What I want to say, this parameter can be large or small in comparison with unity. And let me look at probability distribution and in this case. Actually, why and how Poissonian, that one can prove looking at the properties of coherent states. Right, let me tell just a little bit about this, if you know what is a coherent state. Coherent state is a shifted state of an oscillator, and which can be obtained by a shake-up. So suppose the oscillator is in ground state, then its bottom shifts, and wave function doesn't change, but it corresponds to an excited state. This is a coherent state. And the distribution of number quanta in coherent states is Poissonian. But I wanted to look at just to visualize this distribution. If n average is small, then biggest probability is not to emit anything. And then there's small probability to emit 1, 2 quanta, and the rest, but that you cannot even see. If you increase n, you increase these probabilities, of course. Simultaneously, the probability to emit at 0 is gets smaller. At bigger n, Poisson distribution takes a peak-like shape, which is centered at average number of quanta and spread around a bit. All right, that how does it look like? An important parameter is the average number of quanta. Good, so let us now understand how the curves for this oscillator. Right. It's good to look at differential conductors. Suppose the voltage which is applied to this junction is very small. Then the only process which can go is tunneling is emitting no quanta at all. It is suppressed with respect to non-interacting value. It's an effect of this oscillator circuit, the effect of electromagnetic environment. Right, so for these three different curves, and they correspond to the same values of an average as here. We have rather high conductance in comparison with conductance at high voltage, or rather low. If average number of photons is large, right? Then if we increase voltage, we give possibility to tunnel with emitting one quantum. So first conductance was proportional to P naught. Then at this step, another channel is added. Then at this step, we have a possibility to emit two photons, and so on. So conductance increases in steps, as I pictured in this plot. Fine. Now I can integrate it over voltage. I got current. What I see in this current curves, IV characteristics. At large voltages, all of them are linear, right? Because conductance at large voltage is almost unperturbed by emitting of quanta. There's enough voltage to emit everything. There is some offset with respect to linear law. Okay, it's small for A, bigger for B, large for C. This is offset is precisely the energy which is lost, average energy which is lost in course of the tunneling. This is EC. Right. And these curves are piecewise, and the slope of these curves at zero is the smallest. Right, so it corresponds to this plot. Good. That was for one oscillator. You could say, so what? It looks rather a peculiar case. But the message is that eventually any circuit with dissipation, any electric circuit with dissipation, one can regard as a big set of oscillators. This is something which we learned in the advanced quantum mechanics if you attend this course, but that's also can be explained in simple ways, right? So let us consider a circuit, and we will assume that the only thing which matters is the impedance of this circuit. So, and I look at real part of the impedance at versus frequency. If I have a single oscillator, I just have delta functional peak. Single mode with no dissipation. It's infinitesimally thin. Let me make it a little bit wider. Let me add small resistor here. Thereby, the peak will acquire finite width. Okay, so I have a peak at certain frequency of certain width. Now suppose I have an arbitrary circuit with arbitrary impedance, and I would like to represent it as a plenty of these oscillators so that their impedances sum up. Right? So this is equivalent to approximation of a function like this. Is a big set of such peaks. Here I draw it. So eventually any function can be approximated if we put enough oscillators at different frequencies, and we can thereby we can approximate arbitrary impedance. But we do know how to quantize an oscillator. It means that we know how to quantize any dissipative circuit. So that was a crash course on quantization of dissipative circuits. Fine. Let me understand perhaps not understand, just decide how this function P of I looks for a circuit with arbitrary impedance. How one can prove it? One could just consider the total set of oscillators instead of one, and carefully sum up energy losses from all possible oscillators. Right, so the expression for P of I is rather involved. It is something which depends on energy, but it's better seen as Fourier transform of, with respect to energy, Fourier transform of some function which depends on time. This function has exponential form, and the function which sits there in the exponent in its turn can be seen as a Fourier transform of the frequency-dependent impedance of the circuit. Okay. What are various cases of P of E? In fact, we have seen something like that already for the oscillator. To extreme and not overlapping cases are when we have large probability of elastic tunneling and some tail of energy losses at high energy. That for an oscillator would correspond to small average number of quanta. That corresponds to small interaction. Alternative is as follows. There is no elastic tunneling whatsoever. It is suppressed to zero. And P of E peaks at some energy, perhaps corresponding to the energy of Coulomb blockade. That's the case of big N, as we have seen. Good. In distinction from single oscillator mode, these functions are continuous, but qualitatively they are the same. Fine. Let us see. Oh, yeah, I forgotten to mention that, one can, for instance, continuously change this and continuously change in direction. And there's an interesting borderline between these two extreme cases, which is called Ohmic Environment, right? And it appears to be just an environment which we supply in the first setup we consider. If we, let me get to the first transparency. Yeah, when we have capacitor and resistor, that is supposed to be ohmic environment. So in fact, we are for our setup just at the borderline. Let me concentrate on this case. Here I just wrote the circuit from one. I'd rather use resistance of this resistor rather than conductance. Fine. And it appears to be that this function probability of energy loss at this in this ohmic case is a power law function of energy. It is very unusual. Frequently such power laws are called anomalous. Of course, in physics there's plenty of power laws, but this power law has a continuous exponent. It's not like a squared, cube, or whatever one can see in physical laws. This exponent does depend on parameter, on this resistance. This exponent is directly related to the resistance of this shunting resistor. Fine. Let us see. Here I have plots for P of I. They're not very visible, so let me zoom in. So you can see it better. There are different shapes of P of I in ohmic case. They all power laws at small energy. It's a power law with a negative exponent. Then if one increases the resistance, it becomes zero exponent and positive exponent. And here, I believe the exponent is to the power 20. So it's very much suppressed at lower energies. Right. So the shape is like this. And at large resistances, we rather have a peak at and suppression at 0. Let me sketch this curve. While at small resistances, the curve somehow likes 0. Good. So I just to illustrate the exponential character, I made the same plot in log scale, and it is double log scale. So log of probability versus log of energy. So power law in this case corresponds to straight line, and indeed I see straight lines with different slopes. Fine. That was this probability of energy loss. Now we can look at the current. I derived the formula, and I showed you the formula at the second transparency, how to determine the current. Good, it's a current for ohmic dissipation. First of all, it's rather strange. It's rather difficult to observe, but it is a fact. The other curve of tunnel junction, at least at 0 temperature, is not linear in the presence of any environment. It also requires this anomalous exponent. And basically, it's always smaller than 1. One can see it from the plots of differential conductance. So for all these plots, and they're plotted at very small resistance, moderate, and very large resistance, for all these plots, conductance at 0 is 0. So for any resistance, this dynamical Coulomb blockade actually suppresses the conductance. Fine. They come with different exponents. So for low impedance, for low resist, this suppression is small. But yeah, it increases. It becomes completely visually blockaded here at larger resistance. Fine. All right, so conductance is suppressed by the environment. If one integrates it over voltage, one gets a series of other curves, and they kind of look visually almost the same as other curves for a single mode. Right. So low impedance, low interaction, weak interaction, small deviation from Ohm's law. Larger, high impedance, strong interaction. Then we kind of have a Coulomb blockade till certain energy, and then it grows in linear fashion. So there are two ultimate curves, which are also plotted here, illustrating two opposite limits. We have started our outlining this. Let us see how I'm doing with respect to time. Yeah, let me just quickly go. I would like to conclude the topic of single electron tunneling. What have we learned? We understand that there are strange. We understand that one can make a setup which is intermediate between non-interacting case and Coulomb blockade case. We call it dynamical Coulomb blockade. This setup is characterized by conductance or resistance, which shunts the Coulomb blockade island. This situation is characterized by probability to have certain energy loss. If we know this probability, we can compute tunneling rates. Right, we look at this probability for single mode oscillator, where energy loss is quantized, corresponding to different number of oscillating quanta. We look at different illustrations. We understand there's a small limit of weak interaction and a strong interaction is distinct PFE. Right, and it appears to be that for arbitrary environments, any arbitrary environment can be seen as a large collection of oscillators, and qualitatively, everything is the same. There are two classes of PFI functions: elastic tunneling, no elastic tunneling, and they appear at small and large impedance of the environment. Good. We are interested in ohmic case, a borderline, and in this case, PFE is exponential. And we understand how current is modified in the presence of dynamical Coulomb blockade. So, as promised, it's something in between non-interacting case, ohmic law, and Coulomb blockade curve. Fine. Let me make a break of 5 minutes, and then we can go on. Oh, just a second, I will close the door. What did everything breaks? Fine. All right. Let me go on and let me understand how this environment works in a case of tunneling, not just between the leads, but between different positions. Somewhere, let me make a qubit. Well, a charge qubit, and let me connect it to the environment. First of all, how would I make a qubit? I would just make two islands, two quantum dots with a path and unit in such a way that only one electron is sitting in these two quantum dots. Right. There are capacitances which describe interaction between these two dots. But these two dots are there in the environment, which is characterized by some frequency-dependent impedance. Kind of in simple words, if you move an electron from one dot to another dot and move it back, you excite some excitations in this resistance. There's some energy loss, and that affects tunneling rate between the dots. Right. So how we can understand the situation? First of all, let us consider a decay owing to tunneling between the from excited state to the ground state of this double potential, right? So we apply some epsilon, we shift energy levels between the dots. There's excited state, there's ground state. And if an electron is put in the excited state, sooner or later it will tunnel to the right, and this is decay rate. All right. What controls this decay rate? Let us understand that for this transition to happen, energy epsilon should be given to the environment. The qubit should dispose energy epsilon to the environment. And right, the environment should absorb this energy. So the rate is characterized by probability to have this energy loss in course of tunneling. The coefficient in front of this is just tunneling amplitude squared. That gives us decay rate. Another interesting quantity to look at is to consider admixture of the qubit states. What is this? Tunneling provides some overlap between states in the left dot and the right dot. And it means that if an electron is, for instance, in lowest energy state, it doesn't mean that it's entirely in the right dot. There is a probability, finite probability, delocalization probability to find it in a high dot in the left dot. All right, this probability also depends on the same quantity, but just in integral fashion. Probability of delocalization. Good, so we have the quantities which are affected by environment, and we would like to understand what happens to the qubit if it is embedded in such an environment. The formula which I put here, it is an effective impedance which is felt by tunneling. So it is eventually impedance, low frequency impedance between these 2 points. It differs from the impedance between these 2 points, right? Because everything is divided by this system of capacitances. Right, so it's just electric circuit theory. Fine, good. So let us look at the gases. It appears to be rather interesting transition, which happens at critical value of this impedance, which happens if the impedance, which is felt by charge qubit, is sufficiently large. First of all, how can I see that this transition does occur? I will invoke the formula for probability to have energy loss in the case of ohmic environment, which we have obtained previously. This is power law function. The power does depend on the impedance. Right. From this we can estimate the decay rate in the presence of dissipation. And that also appears to be a function of energy, power law function of energy. But gamma, the width of the qubit level, so that the spread of the levels is gamma, can be compared with energy itself. Right, we understand that it is a good qubit if energy epsilon is bigger than gamma. And if the rate is too large, then the level spreads, it's a bit, and it's already pretty badly defined. So I would not call it a qubit. There is no excited state whatsoever. Good. So we will encounter, in fact, two scenarios. Depending on the ratio between gamma and epsilon at low energy. This ratio is either 0 or infinity. That defines the transition. And at values of impedance which are lower than the transition threshold, we have a qubit. We have two states, and wave function is delocalized between two dots, two wells. At another side of the transition, it appears that our qubit is converted into a classical qubit. So it looks like a classical charge which cannot tunnel, which is in two states, either on the left or on the right. And tunneling and mixing and delocalization of these states is suppressed. So for a qubit in the presence of environment, we have found dissipative phase transition. If the impedance of the environment is sufficiently big, qubit is not a qubit anymore. It is too much connected to the environment. It becomes a classical qubit. Fine. Now let me make yet another change of topic. And let me consider Josephson junction. Again, we will put this Josephson junction into an environment. Simplest environment which we can devise is a resistor which shunts this junction, and we can bias the whole system with voltage source. let us see. We are in superconducting regime, so we don't have tunneling of single electrons, but we do have Cooper pair tunneling. Remember, in phase representation, it is just given by Johnson energy cosine phi. If you rewrite this in Church representation, we understand that this each exponent in this cosine corresponds to Cooper pair transition through this junction, either in this direction or in opposite direction. Fine. Let me see what a Hamiltonian we can arrange. First of all, voltage source. It is important now. All right. If I transfer a Cooper pair through the junction, there's energy supplied by voltage source. So if I plot the energy of the states with different n, I will have a ladder. So for instance, n is 0, 1, 2, 3, so on. I will have a ladder of the states. Here it's this ladder at a constant voltage. I have also tunneling between different ends, tunneling between the steps of the ladder. This is Josephson tunneling of Cooper pairs. How I would include the resistor in this scheme? Well, it has an impedance, and impedance produces fluctuations of voltage at this resistor, and that comes, that adds to voltage source. Okay, that's the Hamiltonian to describe a single Josephson junction in the presence of an environment. Let us see. Let us use again this function P of E. How we can implement it here? It is just a rate of tunneling between these two lateral steps, a rate of Cooper pair tunneling. It is accompanied by energy change of 2 eV. This energy should be disposed to the environment, so the rate is proportional to the this function P of E probability to have energy loss. Right, and the coefficient is just amplitude squared, Josephson energy squared. That gives us current number of Cooper pairs per unit time at a given voltage. Let us see, we see that this is directly proportional to P of E. Right, so the only problem I need to adjust the impedance, which I use for single electron case. Now the charge which tunnels is 2E, not E, so the impedance, effective impedance, has been changed by a factor of 4. Right, otherwise it's the same P of E. And I plot the current versus voltage for different cases. Since it's just a plot of P of E, I copy and paste the plot I use for single electron tunneling. It's just the same function. What do we see? Impedance is big. If impedance is big, there is no current. Current is very much suppressed at zero voltage. Then, okay, then it increases. That's what you normally expect from the current. If impedance is low, then the current eventually grows with voltage. That might seem strange, but we should recall that this is a Josephson junction. It might support supercurrent. At least we find it's in the case of no interaction, very low environment, very low impedance of the environments. So the question is if there is a supercurrent at zero voltage in the presence of environment. Okay, and that is again a question with two answers. And the answer is depends again on which side of Schmidt transition we are. Right. So supercurrent is finite at lower resistances, smaller than this transistor. Then this threshold value. And if environment is has bigger impedance, the fluctuations of this environment completely suppress Josephson effect. So we have two types of R curves below the transition. Current diverges at zero voltage, forming supercurrent. There's a transition, and at larger impedances, the current is just suppressed at zero voltage, and it increases with voltage to some big value and goes down at large voltages. Right, so this is the conclusion. Large external impedance eventually kills supercurrent in Josephson current, in Josephson junction, kills coherence of Cooper pair transfer. Let us see, that was about Josephson junction. How am I doing in time? Pretty good, actually. Let me talk about an alternative kind of tunneling. We have shortly discussed it when we talk about Josephson junction. Let us concentrate on this picture. Let us look at washboard potential characterizing Josephson junction. So as you remember, Josephson junction if the slope of the potential is given by the current. If the current is smaller than the critical one, the Josephson junction can be trapped in different potential wells of Josephson energy. Fine. There's also some tunneling amplitude. Josephson junction is quantum system, so there is a macroscopic tunneling between the wells. All right. Let me make a Hamiltonian, construct a Hamiltonian to describe this tunneling. And also I want to include the environment. Okay, I have to zoom it out again. Right. Let me introduce a set of these phase states. So I just number these potential wells by integer numbers, and the state in the bottom is just n. First of all, let me pay attention to the fact that the current applied makes the states a ladder. Okay, I have it here, I write it here, equidistant ladder separated by the value, actually it is, what is written here, it's proportional to the current. Energy difference. Good. If there is an environment, this produces quantum fluctuations of this current, I included here. So there are fluctuations of the ladder spacing. In addition, I include tunneling. So there's a possibility to jump between different tunneling wells, between different wells in this washboard potential. Fine. I'd like to pay attention to the fact that this construction is very similar to Josephson junction. But we have strange correspondences here. Discrete n for Josephson junction was touch. For phase tunneling, this is phase, or in other words, magnetic flux, it's flux tunneling. What was voltage here becomes current. Since voltage is changed to the current, we expect that impedance is changed into admittance, or let me talk about resistance and conductance. Resistance is exchanged with conductance, strangely enough. So the effect of environment on phase tunneling is provided by admittance, conductance, rather than impedance, because what tunnels is a phase rather than charge. It is a conjugated variable that tunnels. Right. This brings us to the concept of charge phase duality, which can be observed in the same Johnson junctions, eventually in different limits. It's convenient to separate it into cases of current bias junction and voltage bias junction. So in voltage bias junction, we have Cooper pair tunneling. In current bias junction, we have tunneling of phase, tunneling of flux. If you write Hamiltonians, whatever we do, we understand that they are, in fact, equivalent. Both Hamiltonians describe ladder subject to fluctuations. Yeah, that's ladder. The subject to fluctuating spacing between the steps of the ladder, and also tunneling here and here between the steps of the ladder. All right, so tunneling of the phase and tunneling of the charge appear to be completely similar phenomena, dual phenomena. So one could just have correspondence. One can switch between phase and charge like this, between Josephson energy and tunneling in tunneling amplitude in Washburn potential, between voltage and current, and between impedance and admittance of the circuit. Let us relate it to Schmidt transition to different sides of Schmidt transition. And let me interpret it in terms of this charge phase duality. In terms of impedance, Schmidt transition separates the regions of low and high impedance. And as we have learned from Josephson junction, from charge tunneling, for low impedance, there is Josephson current going on, which means that the phase is well defined, it's localized at certain value, right? This is the same for the same result we can obtain if we consider current bias junction. In this case, high admittance blocks phase tunneling between the valves. Phase is localized and we have good superconducting current. Therefore, the charge is delocalized. On another side of Schmidt transition, Josephson current is gone. Zero voltage Josephson current is gone. Phase delocalized. Instead, we have localization of charge. So that, in simple words, no current, so there's a Josephson junction. Phase tunneling, in contrast to this, is not suppressed, corresponding to delocalization of the charge. All right, that was about duality of two sorts of tunneling. Let me just give an overview of all other environmental topics which we have not considered here yet. There are several topics which come about interaction of moving electrons or qubits with environmental modes. We have considered an electron with just tunnels and it doesn't move through the environment. One could also consider electrons moving through the environment, and as you can imagine, the excitations are different there, and Coulomb blockade is escaped in other fashion. Interesting realization of the system are lone wires, which can be made, for instance, from carbon nanotubes, lone one-dimensional wires for electrons. They experience little or no scattering. They're so-called lateral liquids, and the interaction with the environment provides interesting effect in these lateral liquids. There are also fermionic environment where electrons, for instance, in a quantum dot, interact with electrons in the lid. It results in so-called Kondo effect, which provides resonances in quantum dot, and in singularities at Fermi H, when quantum dot, when a level in quantum dot comes to Fermi level, the rate becomes singular owing to interaction. Right. There are also another manifestation of environmental interaction with environmental modes, either electronic or photonic excitations of electrical circuits. And that we will discuss in the next lecture when we talk about decoherence and relaxation. Decoherence and relaxation is important for quantum mechanics to survive. One high decoherence, high relaxation just kills quantum mechanics in all the phenomena we consider. In principle, I could start with this last lecture, but that would be rather boring. First, to talk about inhibiting mechanisms, and then about the whole beauty, the whole variety of effects in quantum transport. So I left it for next lecture. We will have here two sessions. There will be a lecture next week, and some date, I forgot, somewhere end of May, we will have also a problem-solving session. With this, let me thank you for attending, and let me finish this lecture.